These are the solutions to Chapter 5.4 textbook homework problems. Um, in order to do the problems on Chapter 5.4, we need the formulas here. We need to reference the conditional probability formulas and the general multiplication rule. So that's what we'll do. So let's go ahead and look at number 15 to start. I'm going to write down the information given to us. According to the U.S. Census, 8% of 16 to 24-year-olds are high school dropouts. So what we know now is the probability of being a dropout is equal to 0.08. We also know that 2% of the population are dropouts and unemployed. So the probability of being a dropout and unemployed is equal to 0.021. And then the question is asking for what is the probability that a random selected 16 to 24-year-old is unemployed given that he or she is a dropout. So the key on this one here is, according to our notes, is this given part. We're now limiting the population. Instead of choosing from the entire population, we're only considering those people who are dropouts. So the notation for that gets written a little differently. We're looking at the probability that someone is unemployed given that they're a dropout. So once we know they're a dropout, what's the probability they're unemployed? And so that becomes the question that we're answering. Unemployed. And here's the notation we use. You got to use that bar. What's the probability of someone being unemployed given they are a dropout? And so if you look at this, we're trying, how do we calculate it? We come back to this formula over here. You can see is the conditional probability. Given is that condition. We're putting a condition on the population. Instead of everyone, we only care about the dropouts. So what's the probability of being employed given that they're a dropout? And notice that notation we have this formula here. So our answer to that is going to be 0.021 divided by 0.08. And then you end up with an answer of, after you divide those, you should end up with an answer of 0.263. So we're just applying that formula there to get that, and I wrote the information. Let's go ahead into the next problem, number 18. A little bit longer. Let me zoom in here. Okay. And so now we're considering adults 18 or older. We're asked whether they use social media. Here is the information. So we got to be able to read the table. Use social media. 530 people were asked. Do not use social media and the age of those people. And so we can get an idea of the distribution of who uses social media and doesn't based on age. So let's answer some questions. A, what is the probability that a randomly selected adult uses social media given that the individual is 18 to 34? So I'm going to abbreviate. They use social media given that they're between 18 and 34. So that given part, now I'm not going to look at the entire population. I only care about this total population. So my answer is, what's the probability someone uses social media? There's 117 out of 150. And so then that would be the answer we're looking for there. And that should be 0.78. So that's B. Again, this is conditional probability. And in this case, what we're looking for, in this case, we're kind of looking at this formula here. The number, if you kind of looked at this formula here, that's what they would follow. But again, the given is that probability F given E. Notice we're dividing by the number that fall in this category of E. And so maybe I should write it here real quick. The probability of E of F occurring, given that E is already occurred. You look at the formula here. It can also, we can determine by the number that are in E and F divided by the total number that are in E. And that's the formula we have here. And so where does 117 come from? Because that's the total that were social media and 18 to 34. And the number that belong in E is the situation 18 to 34, 150. So that's where we're getting those values from. What is the probability? Selected adult. Selected adult between 18 and 34, given the individual uses social media. So what's the probability? So we're reversing the question. What's the probability someone's 18 to 34 given they use social media? And so in this case, what's going to go on the bottom is the number that are in this category here, which is how many use social media. That becomes our new population. We're only interested in that 338. And how many of those are 18 to 34? And that's 117. And so in that case, that would be your fraction. And then that fraction gets turned into 0.346. Part C, are 18 and 34-year-olds more likely to use social media than individuals in general? And so in order to answer that question, we want to look at the total amount. We're going to compare 18 and 34-year-olds. And we are 18 and 34-year-olds more likely to use social media than individuals in general. And so in general, right, we'd look at how many people use social media. That would be 338. That's how many use social media out of 530. And so then that number is equal to, you have to divide that. That looks like that's 0.638. And then we want to calculate 18 and 34-year-olds. 18 and 30-year-olds. How many use social media in there? And so this is the answer for part B. So what's the answer for 18 to 34-year-olds? It's this one, or how many 18 to 34-year-olds use social media? And that's 0.78. So the answer to this question, the answer is yes, because we look at these percentages. Only approximately, that's a 4, 34.6%. Wrong one. Approximately 63.8% in general use social media. And in this case, we have about 78% of 18 to 34-year-olds use social media. And again, I got that from the original question on top. Okay, let's go ahead and look at problem number 21 from chapter 5.4 homework. There's 2 questions being asked here. So the first thing we need to know is the information we need. Suppose that you just received a shipment of 6 televisions. 2 are defective. So here are your TVs. There's 6 of them. And we then know that 2 of them are defective out of that. So what we know before we do any calculations is that the probability that the television works is going to be 4 out of 6, and the probability not work would equal 2 out of 6 to start off with. So first question, what is if 2 televisions are selected at random, compute the probability that both televisions work. And so what we're looking here, we're looking for the both work. And so what that is the same as saying, what's the probability that the second one, the second TV works, given that the first works also. That's what we're doing. It's really a sequence of events also. It's also kind of, we're dealing with this, we can actually think about that two ways. Both work, that's one way to think about it, and that's equivalent also to saying the probability that the first works. The probability that the first works and the second works. So it's kind of works in that they're kind of all equivalent statements. And that's what gets confusing about this problem. But it's also a chapter 5.3 problem too, where it's a sequence of events. So this is it's a simple problem, but complex at the same time. All these are equivalent ideas. And so the way I think about it is it's more of a sequence of events. What's the probability that the first one works? And so I'm looking at that one there. And so that would be equal to the probability the first works. Sorry, let's go with this one here. Looking at the E and F, right? The probability the first works. I'm not running out of space here. Probability that the first works times the probability that the second works given the first works. And so kind of looking at these ideas here. And so now that I think about kind of this notation, let's handle this here. This one gets a little bit more complicated to explain in this way. So for now, let me re-explain this here. Let's take this one out. The probability of both works is equal to the probability the first works and the second works. And so then we look at this notation here, probability E and F. It's probability E times the probability F given E, in which I wrote here. And so to get that answer, what's the probability the first works? That's just going to be 4 out of 6. That would be 4 out of 6. Times the probability the second works given that the first one worked. So here's the subtle trick here. On this one, I'm going to multiply the probability the second one works, if we know the first one works, is that we know this happened already. So then now there's only 3. This one works, so now there's only 3 out of 5 left that works. Since one of them works, if this one works, the one we chose works, then there's left 3 out of 5. And so then our answer is 12 out of 30, or 0.40. Okay, and then what is the probability that at least one does not work? And so what we learned, at least one no work. We learned in the previous one, this is an idea from our notes here, that this is an at least one probability, which then it's 1 minus the probability that both work. So that's the little number trick we're using in this case. And we know the probability that both work is 0.40. So our answer is 1 minus 0.40, or 0.60. And so again, sorry for that quick, this is a little bit another more advanced way to think about it. So let's stick with this here. Okay, moving to problem 36. The following data represent political party affiliation. Here are the situations we need to consider here. Are the events. So in the first situation, we're going to ask this question. This is one of the last details in our notes for chapter 5.4. How do we check to see if something's independent? And so let's go ahead and look at that real quick. So to answer the first two questions, we need to recall this idea here. Two events are independent if the probability of one event given the other one has occurred is equal to the probability of that event, meaning that F had no influence over that, or vice versa. Depends, who knows what event you're talking about. And so we want to make sure that again, what that says is the probability of E equals the probability of E, meaning that F had no influence on it, which means that E and F are independent. And so F does not affect the F occurring does not affect that probability at all. And so that's what we're looking for on our problems here. And so the formula we need is if this is true, then this means independent. Okay, and so are the events Republican and 34 to 40 independent? So let's calculate this. Let's see, different color. The probability of being a Republican, given that your 30 to 44 is equal to, so we're looking at only 30 to 44, and so this is 340 Republicans out of the 30 to 44 people, because that's the given. I'm only considering that population. And so then we have that calculation there to look at, which we'll do. And then we want to do the probability of just being a Republican. What's the probability of being a Republican? So that would be 2,200 divided by 4,000. And then we want to compare those values with each other. And so remember, they're independent if these two are equal to each other. They're not independent if they're not equal to each other. And based just like looking at that, it doesn't look like they're going to be independent, meaning they're not equal to each other. And so that looks like what's happening. This is a 0.470, and then this is definitely bigger. So we'll just calculate it real quick. And so then you get 0.55 right there. So yeah, so the answer is no, they're not. And there's my justification. That's part A. Part B, are Democrat and being 65 plus independent. So the probability of being a Democrat and then 65 plus, given that you're 65 plus. Let's see what that is. So here's 65 plus. So there are 10, 20 there. And how many Democrats are in that group? That's 459. And so we'll do that calculation to see what its value is. I get 0.45. And then we want to check to see is what's the probability of being a Democrat? And so I have 1,800 over 4,000. And you get 0.45. So therefore, since they're equal, we say these events are independent. Okay, let's go ahead and answer C and D. In order to answer C and D, we need to remember what mutually exclusive means. Another word for that was disjoint. And that means there's no outcomes in common, that there's no way that those events can happen at the same time. That's different than independent. And so for C, can someone be 17 to 29 and 45 to 64 at the same time? Those events are disjoint. They're mutually exclusive. So the answer is yes on that, because you can't be both at the same time. D, can you be Republican and someone between 45 and 64? And the answer is you can be both at the same time. So those are not disjoint. So the answer is no. That's it.